All right, we've reached Thermochemistry 5, where we're going to talk about calorimetry, which is a process for measuring thermochemical processes. So a calorimeter is a fairly simple process in any high school chemistry class. It's almost always the case that we just use styrofoam cups. A calorimeter is just a thing which insulates a particular process against heat loss. So if we look at the picture on the right, this is a standard constant pressure calorimeter. And so what you have in this situation is number two is some kind of a stir rod to keep the thing well stirred. Number one is your thermometer. Um, Everything else is kind of showing you that insulated system where you're going to have one container inside of another so that there's very little heat loss to the surroundings for everything taking place inside that internal container. The picture on the left is what we refer to as a bomb calorimeter, and it is referred to as such because it is a constant volume calorimeter. So you have this container inside a well insulated secondary container that has a water bath in it that we're going to measure the temperature of that surrounding fluid as a proxy for the temperature of the system. We're going to keep it well stirred. And then you look at that ignition box. A lot of times what you'll do in a bomb calorimeter is you will measure some particular process by igniting it, keeping it at constant volume, and then measuring the heat that comes off. That allows us to figure out what kind of chemical process or what kind of heat chemical processes produce. This, by the way, is how they sort out the caloric content of food. So they'll put a weighed out portion of food in that sample cup. They'll ignite it, burn it, and then measure the amount of heat it gives off. And so that tells you what the energy value is in the chemical storage in that food. One of the reasons calorimetry works, right, is because we're going to establish ourselves a system. We're going to establish surroundings, and we're going to measure energy flow either from the system to the surroundings or vice versa. And any energy lost by the system will equal the energy gained by the surroundings or vice versa. And this is a simple consequence of the law of conservation of energy. It's a feature of the universe. During any physical or chemical process, the total energy of the universe remains constant. Energy is neither created nor destroyed. Again, in Chem 2, we'll talk about chemical processes with respect to calorimetry and thermochemistry. Right now, we're still focusing primarily on physical processes. So again, we'll look at that heating curve. We're looking A, B, C, D, and E, F are all temperature change. So we have our CP of solid, CP of liquid, CP of vapor. You have your heat of fusion, your heat of vaporization going to the right. You have your heat of condensation, heat of solidification going to the left. Of course, we could be on a different part of the heating curve, the phase diagram, or at a different pressure, and these values would be at different temperatures. If you're below the triple point and you go directly from solid to vapor without going through liquid, you're only going to have one flat part, and then that C to D line will just be gone. And so you'll have heat of deposition going to the left. You'll have heat of sublimation going to the right. But this is our standard pressure heating curve for most pure substances. So let's look at how calorimetry goes. So we have a 150 gram sample of metal that's at 134.0 degrees Celsius. It's added to a 300 gram container of water. That's the water, the 300 grams of water, not the container weighing 300 grams, is at 15 degrees Celsius. The temperature of the water is going to raise to 18.3 degrees Celsius. What is the specific heat of the metal? This is often a way that you figure out specific heat of unknown metals. So here we go. We're going to drop that hunk of metal into our calorimeter. We're going to make sure it's well stirred. Since the metal is at a higher temperature than the water, the metal is going to lose heat to the water. Well, what's going to happen to the metal? Well, its temperature is going to go down. What's going to happen to the water? Its temperature should go up. How long will that process take place? Well, the process is going to take place until they're at thermal equilibrium, until their temperatures are the same. When there's no more temperature gradient, there will be no more heat flow. So notice this problem does not directly tell you the final temperature of the metal. And I'm going to let you keep that in your head while we continue to work. But here's how you set this problem up. You have a certain amount of heat lost by the metal. And it turns out that's exactly the amount of heat that was gained by the water. So Qm equals Qw, except for one little problem. Metal's losing heat, right? So it's going to be a negative value. And the water's gaining heat, so it's going to be positive. And you can't have an equation where a positive equals a negative. That's a does not equal, not an equal. So to fix this, we have to make sure we drop a negative on one side or the other. It doesn't matter which side, right? Qm is negative, Qw is positive. So if Qm is negative, negative Qw will also be negative and they will be equal. Or I could just as easily put this over there. If Qm is negative, the negative of Qm will be a positive number, which will equal the positive value of Qw. Okay, so 134 degrees Celsius is well below the melting point of most metals. So we're definitely dealing with just a temperature change here. The metal's temperature is going to decrease mCp delta T. That's the Cp of the metal. The water's temperature is going to increase mCp of the water delta T. And then we need to make sure we remember that negative sign. Again, doesn't matter which side you put it on. We'll keep it on the left this side. We have masses for both substances. And then let's go back to that delta T conversation. Delta T is T final minus T initial. So what would be the final temperature of the metal? Well, the final temperature of the metal is going to be the final temperature of the water. You'll measure the temperature of the water as it increases when you add that hot piece of metal until it stops increasing. The point at which it stops increasing is where you assume you've reached thermal equilibrium. So both the metal and the water should have the same final T. So here is our equation then. Negative 150.0 grams times the Cp of the metal, which is what we're looking for, times the temperature change, T final minus T initial. It's going to equal the 300 grams of water times its Cp, and you'll want to look at your data packet for that, 4.186 joules over grams degrees Celsius. And then the temperature change of the water, which is final minus initial. So if we're to simplify both sides, the delta T value for the metal is going to be negative. So that's going to get rid of your negative sign. Your delta T is going to be negative, and then you have that other negative, so they'll cancel out. Multiply that by the 150. You're going to be at 4 significant digits on that left side of the equation. So I'm going to take my calculator value, but I'm going to underline the 4th sig dig. Cp is still the unknown, so we're going to plug that in there. And then 300 grams times 4.186 times the delta T. Everything on that right side is positive. That delta T is going to reduce you from 3 sig digs on those temperatures to 2. And so we have 4,144 joules. Again, if we think about the units here, we have grams times degrees Celsius on the left. We have joules on the right. When we solve for Cp, we're going to divide both sides by that 17,000 grams. Degrees Celsius. So your units are going to be joules over grams degrees Celsius, which of course are the units for a specific heat. You got to make sure you round to 2 significant digits. So you might do that work on your calculator. If you haven't already done it, you can pause the video real quick till you finish. Get yourself some sig digs, some units, see where you end up. And you should get about 0.24 joules over grams degrees Celsius. This is reasonable for a metal. If we go back and look at the video that had our list of CPs of metals in joules per grams degrees Celsius, most of them were decimals. If this had come out to be 24, 30, 100, 0.0007, you might be a little bit worried about your calculations. But if you go back and look at a list of CPs, that seems reasonable for the CP of a metal. If we had known this to be a pure substance, which we don't, we could certainly check a table of CPs and figure out what it is. Of course, the metal could be any number of alloys, and the CP of alloys are going to vary depending on percentages. So specific heat as an identity is only good if you have a pure substance. So there you go, basic calorimetry calculation.